back to desgn380. This is a video on simulation. Hidden inside of it is some discussion about flow lines. I'm going to go ahead here and upload our part. Probably be better if I triggered the right thing. So while this uploads, we're going to run into some problems here. I've made this video a few times, actually more than a few times. Hopefully this one goes better. The goal here is to try and do simulation and think about the flow lines in the background. We're going to make some decisions in the design of the parts, and it's based on Orlov in volume 2, figure 110, which is on page 140 for those that have it. The goal here is to have a look at this sort of thing. Let's make this a little smaller. Oh. The goal here, so you can't see what I'm doing. I'm trying to make this smaller. Come on now. So tiny. Close enough. We've got D and E here. I've modeled them both. We're going to run them both through the sim. The dilemma we're going to run into, just so we know what's coming, is we're going to discover that these struts are around this keyhole, or however you want to think of it, are a little bit too thin. The simulation is going to show us, I hope, what we know from flow lines. Flow lines are going to come in at the threads here. The load is up in the top. Going to come in and go around. There's a little tiny fillet here. We expect the flow lines to be quite bent. As we know, bent flow lines introduce a stress multiplier. The more bent, the higher the multiplier. The idea in the second version, E, is that the flow lines come in, go through this waist, neck, same as the other side. But instead of taking a sharp turn, they go up and through, so there's a smoother flow. Unfortunately, we see the flow lines coming in here, and they have to kind of do an S bend because this is quite thin. We have some options. We could try moving this inboard, or we could thicken this. The other effect we have, we know from flow lines, is the denser they are, the higher the stress. Or basically, the smaller the area they're flowing through, the higher the stress. Makes sense intuitively. See here that this is about twice as thick as the strut. We're going to run it as is to begin with. But as one of my colleagues pointed out in the previous video, we're going to get an unexpectedly high value here, which kind of starts to break Orlov's point. We're going to use our knowledge of flow lines and work our way through. So, given all that, let's go ahead here and run this file. It'll convert it over. If you see no history, we would like the history. Right click at the top here. So right at the top of the part, capture design history. It'll give us it'll place some files, bodies, and make components. If we press Shift N, back and forth, it toggles the colors on and off. I'll leave it off for now and close the data panel. Right now we've got, let's have a quick look what we've got. Got some fillets around the outside of this strut. We've got a fillet on the inside of that hole, or keyhole. And importantly, probably the two fillets that we're mostly interested in both parts are these guys. This is going to be quite a problem. The flow lines are going to try and bend around here, so we're going to keep an eye on this part in particular, secondary the rest of it. Also keep in mind this discussion about the flow lines coming around. It'll have to go around this fillet, curve up and through this strut, but importantly, the other one, the inside flow lines, will also have to do, so we'll end up with a sort of an S bend. This causes a KT, which may not give us the strength or the competency, the strength that we would wish. Go to simulation. Go for static stress. For now, that's good enough for us. Have a look. Now, I'm not even going to start doing the mesh. Even at this very coarse mesh, one of the big sort of things we should always keep an eye out for is threads. Don't want to model threads inside of a simulation. We don't want to mesh them in particular. One option is to go back to design and delete them. Then we lose it. Another option is in the simulation to use a simplify. the remove feature is based on size, more or less. Kind of works great if everything is regularly sized and all the rest. The other option for us, which is going to be better here, is to modify them by removing them directly. Now this doesn't remove it from the design, it just removes it from the simulation model. Roll in a bit. I want to get rid of the minor diameter. Select those three, so the minor diameter and the bracketing helical phases, delete. Do it on the other side. Minor diameter, bracketing phases. Because they're helical, select them all, delete, close. Sorry, I'm a bit sick, so if I lose my voice here, it's, it's the illness. We've got some work done here. The next thing, the flow lines are going to flow through this strut. These fillets are not going to do very much. Just as a way of seeing how this works, we can also simplify back in design. Notice when we go back to design, the fillets are still, the threads are still in here. Under modify, simplify, remove, again, similar, almost identical command that's there. And it will pick surfaces that are tangent to each other as a chain. There we go. So make sure we get them all. There's some around the back. So if you're using the same model as I am, you should see around 40 selected. Do not delete these guys. We're interested in these. Delete them. Close. Also left these fillets intact. What diameter is this, or radius, right? Down here at the bottom right, if we select anything, it shows us a feedback. 1. I might like that to be repeated, put back in. So rather than trying to modify the simplification, why not just put them back? F for fillet is a shortcut. Give it a standard, rolling ball is fine, and you can select right through if you know where it is. 1. Okay. Done some good work there. Let's go back to simulation. Not bad. One thing is this little edge. Sometimes that creates a problem in the mesh, and it's tempting. We can try this, see if it works. Try and get rid of that little edge there. Press delete, see what it does. It may not work, right? So there, it's kind of stuck. This is caused by this fillet being pushed up against the edge here. One thing we can do, since we're at it, our fillet's in here. Before we do this, let's pull back our history 1. So we should expect to see the fillets disappeared, right? Let's try just deleting this whole phase. Interesting. Pull the fillet back out, edit the fillet, put the fillet back on. So let's see if we can, now sometimes your preview is not working. You can hold down, in this case I'm holding down Command or Control in the PC. Yeah, we end up with that same loop edge. Not much we can do about that. So just keep an eye on that. If we want, we can just delete. We can undo that stuff by just pressing Control-Z. That's because, oh, watch out for the watch out for the history running here. So you can see here's our delete phases. Just Control-Shift-Z to go back forward. Again, if you're kind of getting stuck, that's not our fillet. We can delete that out of the history, get our fillet back. Sorry about that. A little bit confusing, but our history is now back to normal. Back to simulation. Run the mesh. Just turn it on the first time. If you've got everything kind of under control, it should go fast. I'm used to this computer. That was speedy-ish. Get a reasonable mesh. Fillets are in here. It's nice. And what we should see is as the density, the mesh increases as it hits curves. What's going on there? It's a bit rough, a bit loose for our sim. So let's go ahead here and have a look at how to modify them. beside mesh, if you hover, little pencil appears, click that once. You can decrease the size. So for example, this is like a scaling event. This will give us 7%. 7% of the length mesh will appear. So the less we have here, this will be about 100 per length, 10 per length, somewhere in between. Let's go 4.7. That'll put the mesh out of date. Generate mesh. Should see it getting a bit tighter. A little slower. It's not bad, better. This, you want the inside loop of things like these sort of open, I'm sick, brain fog. What's this thing? Cylinder. You should try and have both of these faces about the same level of mesh density. They're quite loose, but they're similar, so it's not doing too bad. Problem is, we would like it to be quite a bit denser around this point of interest on both sides. Potentially up in here as well. Best way to do this is to, you can use local mesh control. But one thing that we are probably interested in is controlling how it runs around curves, the mesh. I want it to be denser around the curves. This guy right here under advanced, if you hover, smaller angle produces a finer mesh. I'm going to go down to say, if I hover I can see it 40 degrees. Over in sort of, if you use Nastran standalone, which is what's running here, their default is actually 20. So somewhere between 20 and 40. Let's try about the middle, 35, 30. Let's try 30. See what that does. Mesh goes out of control, out of date. Generate the mesh. Keep an eye on this guy right here. A little bit longer. Interesting, that's okay. That's not. Right, so there's a problem here with the change in geometry in this part. Let's have another look. I'm going to make this a little smaller. So I'm at 6 right now. Generate the mesh. Sometimes it gets a little stuck because this is a kind of not straight. This is like a saddle shaped fillet because it's going around this curve. This is a flat curve. Sometimes you have to toggle it a little bit, trigger it by adjusting the overall zoom, if that's how you want to think of this. Oh, wrong button. So up here, the model base size is how you would control how it patterns across this face here. Sometimes just making it a little bit smaller in concert with this can have quite a bit of an effect. So it's not a necessarily linear thing. Let's have a look at the mesh. See here, this is a little small. It's not something we're ultra interested in, but again, not great. Let's look at the mesh settings. We can talk about mesh ratios, aspect ratios, and all that sort of stuff. But again, we can keep going down here, trying to get our sort of larger scale mesh smaller. We now have similar mesh size. It's not too bad. It's like 4 rows across. It's not bad at all. This is again quite dense, but not too bad. Again, inside these fillets, we're looking at high mesh density, but that's probably where we're going to have high KT because of flow lines bending. It's all fine. Let's run that guy. But first, we have to do some work on getting ready. Materials. So I'm going to move from left to right across the ribbon, or top to bottom down the browser. Let's use the ribbon. Right now, ASI 1050 is a known thing. However, sometimes there's lots of layers and types of it. Sometimes it says to us, let's really make sure we know what we're doing here. Pick steel all the way down, ASI 1050. It doesn't show up immediately until you pick, so if you've shift selected both, you'll get them both. Yield is good. This means a safety factor of 1 in the result will mean it's gonna permanently deform more or less perfectly. Maybe just right here. If it goes slightly beyond, we'll get a deformation. That's fine for us. Still not perfect, not ready to go yet. Loads and constraints. Let's lock these two threaded parts. They're not threaded anymore, but we know they are, to the universe. We can use this degree of freedom view, DOF. Green is good. We can also run with potentially fixed cyan quite easily. Next, we need a load. We've been in a discussion, the instructors in this course. 4 kilonewtons is good. Targets. There is a slight bug in Fusion. It's not a big bug, but it's a bug nonetheless. Sometimes when you select multiple faces, it distributes the same load across. Sometimes it splits the load, and then once, in the previous video, it actually turned one off, which was odd. So let's do one at a time. Make sure your icon is pointing upward. Do the same again. You can right click and repeat structural load. 4 kilonewtons. Type out 4K, capital N. Goes black, meaning good, and hold on. Was that right? It looks different. That's not right. Let's double click. 4, no bearing load. Loses the load sometimes for, oh, not big K, little k. And it's pointing correct. Same icon. And the loads are now collected inside the browser. There, 1 and 2, along with our fixed. Ready to go. Let's have at her. Solve one study. And let it go. Come on. It's thinking. There we go. It sends up and starts solving. If we want it to go faster, we need a non-education account. Then we have a potential of it going faster. Depends how busy the servers are. And now we just sit and think about other things for a while. And we're back. Let's see what we've got here. We can change the size of the legend here. Let's make it large. We can also turn off Bandit. Bandit is fine. What they're saying here, I suppose we should stick with this for a second. What they're saying here is above 6 is really safe. Between 6 and 3 is safe. Not too much material, not too little. Under 3 to about 1 is getting borderline. It's okay, but not bad. And here we have a minimum right at 1. So we would be right on the edge of getting some deformation somewhere. Now, let's see where those are. Often it's hard to spot them. We get an absolute minimum, but what is that compared to this guy? So we can pull this down and see where our volumes are still allowed. You can see it's in the spot we would expect. Also, the so-called safer version is if it's not equally bad, it's slightly worse than our so-called bad version. This is supposed to be not so great. This is supposed to be better. What we're seeing right now is a bunch of different combo of things here, so we have to kind of go through this bit by bit. If we look at our mesh, we can see that it's based on the mesh, and it's basically running through a bunch of calculations. This is a magnified deformation. Actual, undeformed, slightly magnified, which is best. You can go all the way to crazy stuff. This is clearly not what it's doing, but it shows you the trend of the bend or the movements. I usually use, if I use adjusted at all, 0.5 is enough. You can see the pretzeling here, which is what Orlov had predicted in his diagram. That's it right there. So we're getting the correct shapes, is sort of a pretzeling. But we've got some problems here. This is not what we would hope for. Getting quite a bit of bend in these maybe overly thin strutty type parts. So we are getting errors in where we thought. One way, while we're still here, is to see each body independently. If we open up the model components, we can turn them on and off. So here we have a minimum 0.93, which is essentially 1. And over here, our minimum is 1.006, quite similar, right around 1. So we'd be worried about permanent deformation at both of these necks where their fillets are attached to the upper structures. Nonetheless, it's all fine. And it's tempted to run off panicking, like Orlov's wrong and all that sort of stuff. The diagram might be wrong. His argument, I think, is correct. What we're trying to do before this beginning is talk about flow lines. In this one, there's nothing we can do really. Could maybe increase the fillet, bend, straighten out the flow line in this very particular place. But apart from that, we're kind of stuck. Here, we've got some flexibility. Here we've got the flow lines coming in at the threads, up through the neck, through this bad spot, this tight fillet. And then, not helping things, it goes around into a kind of an S shape. So let's look at it undeformed. Flow line comes in, comes around and out towards the middle, or the lower part, comes through the middle of the neck, decides which way to go, goes this way, and it bends around as well. So we get this trend of S bend. Might be better if we went in and came out straight. Let's do that. Back to design. Can we just adjust this guy? Now we're all running off screeching again because we think, oh no, here comes sketches and extrudes and all this sort of stuff. Fusion has a good little tool called press pull. What it does is it tries to modify what's already there and just the same but a different size. Importantly, if you look closely at this, I don't know if we can zoom in, it takes the fillet with it. Let's pre-select this time. I've made this made this video a few times. I want to move these 3 faces. Don't want to move the fillets size-wise. Press, pull. Now, you have to be careful of this. It does it live. It's a lot of calculations. It's hard. So do it gently, carefully. You'll notice it's kind of pulling in. I'm going to cancel because I want to know how far to pull. I for measure, I for information, really. It just runs on clicks, the way you select. So if I select this face, it shows me what it knows about the face, and then if I select another, it shows me what it knows about both, and the relation they're on 5 millimeters apart. Fine. You don't have to exit, just keep it active, but select away. What about these 2 guys? 10. So if we keep that in our heads, that's 10. The previous one was 5. Let's check again. 5. So if I click that once, it selects. But maybe if we made this about that thickness of this, transferred it down to here, we'd be better. So let's do that again, like we were doing with the press pull. Because this is a lot of work, I tend not to try and do this too much on the fly. It's fun to drag, but it should be better to just type it in direct. Notice the fillets move nicely. They're still the same size. You can say okay. Doesn't give you any history, which is kind of good and bad. Fillets are still gone. Sorry, the rounds. So everything's looking good. This should give us better control of the flow lines. Another option here would be to change the draft of this, which is a little more work, but this could be another, like if we get kind of good results, maybe this is the next step. So we could change the angle of this, maybe tighten up the size of this small surface here. This surface is probably there for a reason. It's to stop the thread going too far. It's like kind of a hard stop. But maybe it's not that important, right? So we could change the draft. That would be maybe a potential thing later in the effort here. Let's go back to simulation. Our results are out of date, so let's finish results. And we have to generate the mesh because we changed the volumes. Reasonably fast. And it's doing a kind of double think here because of these rounds. Fillets are quite nice, tight, nice, not too much, not too bad, about the same. Inner and outer loops about the same mesh, and some match between the size of the mesh. Now, again, for a final simulation, this might not be tight enough for the mesh, but for now, to save time, this is probably good. Let's run it again. Still, everything's kind of good. Our bearings are still there. Bearing load, sorry. And our fixed is still functional. Off it goes. And now we wait again. And we're back. Let's see what we got. We have a reasonable, interesting result here. We're looking at safety factor without the bars. If we turn on the bars again, we can do that. Bandit, sorry. See what's going on. Now this time we have a slightly different answer. Again, for me, I've been waiting for the runs to go. See a thicker strut here. We can turn off these bodies one after the other. Our minimum on this is up to 3.4. Our minimum on the first one, the so-called less acceptable or less good solution to this geometry, is down still at about 1, slightly below, more or less the same as what we had before. So no real change here. So this is about 1.1 safety factor. So we are getting close to permanent deformation. But if everything was perfect, which is borderline sort of assumption, then we would be okay. But any deviation to our expectations would maybe end up in a permanent deformation. This one is safer on this side. Let's have a look. Change back to smooth. If I start pulling away, you'll see a lot of the parts are actually in quite high safety, meaning they're probably overbuilt everywhere around from this problem area, but for now, let's not worry about that. And we can see that it pulls away quite a bit faster in what we're calling E, the strutted version, down to our sort of 3 to 1 is kind of our sort of danger area. In this one, We don't have anything in that danger area here. We've got that standard tight fillet that we were worried about from the very beginning is between, or it's under 3. So this is problematic. Let's have a look at stress. Now, these sorts of shapes are interesting. The pretzel comes out of sort of an induced bending. If you pull up from the bottom, it's time to get rid of the low stresses. The lock to the universe disappears first. It's more or less 0. And then you'll see it pull away. This, if we leave it right here for a moment, we can see the flow lines in a way almost, they're kind of flowing up through here, through the strut, up into the loop and around the top. There is an induced sort of compression sort of thing going on in here at the bottom. And we can kind of see that by magnifying the deformation. So if we look at actual to deformation, if we make that fairly extreme, we can see the difference in the bend or the trend. This is bending, even though the bend is tiny, this is magnified like crazy, but this is bending way more than this. So D bends way more than E. This is what we would kind of expect. We get the shape that Orlov expected, the loop, the pretzel, but this has much more sort of control still connected here. So we can see the flow lines in a way running around. The flow lines are not so visible yet. If we keep going on the pair, we'll see on the left, we start to get the same sort of thing. It's jumping across, going to the inside and then up to the top. Arguably, this is what gives us the pretzel approach. But this is the sort of kind of watch of bending. When we get this hollowed out, where the outside and inside fibers are stressed, this is a signifier of bending. We have the same bending on the other side, this guy, but it's obviously way less. If I can pull it, there we go. So it happens faster and then disappears quite quick. So we've got quite a bit of bending running here, and my computer's not very happy right now. So we are doing not too bad here. We get the result that we expect. Let's have a look. Oh, getting the jank. Let's finish the results while we can. Again, quite a slow response here. Now, if we wanted, what we could do from here is continue on with the logic of the flow lines. So if, if we go back to design, I hope, we can have a look, slow and steady. Have a look here. Let's use the view cube because it's getting a bit laggy. What we could do here is talk about how to increase this yet more. So if the logic of the part required not so much of a platform underneath here, we could increase basically the draft or the angle and point these struts closer down and at this neck. That would probably help us. But the thing is, right now we're at a kind of 3.5 safety factor minimum on this guy. So arguably this is not too bad the way it is. So there we go. That's our video. That's our final results. How to kind of deal with Orlov, use the flow lines inside of our heads to redesign a part based on some, hopefulness in a way, like we wanted to see this better, and then we found out essentially that the Orlov diagram could have had a little bit more editing perhaps in the beginning. Next question is, do we need this void at all? Arguably yes. Could we move this plate or the flat part down to improve load management, and could we lightweight this guy by maybe making the entire thing smaller diameter based on the 4 kilonewtons? Thanks for watching. over to you. This is the end of the video.